Okay, this is Math 314 and 615 Algebra. And the first lesson is one of the most important methods to prove things in mathematics, and that is called mathematical induction. And the idea of mathematical induction is very simple. Suppose there's some statement or some sequence of statements. So for every number n, there's this statement, a proposition P of n, and you want to prove that it's true for all integers n, all positive integers n. So we have some proposition, statement, P of n. For n, it could start at 0 or 1 or 2, it doesn't matter. Say we start at 1. And we want to prove P of n is true for all n. So there are two steps. The first step, we prove P of n is true in the first case for n equal 1. And the second step is we prove that if P of n is true for some n, then P of n plus 1 is also true. So from step 1, P of 1 is true. From step 2, if P of 1 is true, that implies P of 2 is true. If P of 2 is true, that implies P of 3 is true. P of 4 is true. If P of 3 is true, that implies P of 4 is true, and so forth. So we conclude P of n is true for all n. So that is the framework of the principle of mathematical induction. And let me give two examples of how we use this. So example 1. So example 1, it's based on something that many people discover for themselves and at some point and think, oh, that's really kind of interesting. So we have two interesting sequences of integers. So we have the odd numbers. 1, 3, 5, 7, 9, 11, 13, and so on. And we have the squares. 1, 4, 9, 16, right? 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 4 squared. 25 is 5 squared. 36 is 6 squared. 49 is 7 squared, and so forth. So we have these two interesting sequences. And we can make the following observation. If you add 1 and 1 is 1. If you add 1 and 3, you get 4. If you add 1, 3, and 5, you get 9. If you add 1, 3, and 7, you get 16. So let's say that 1 squared equals 1. 2 squared, which is 4, is 1 plus 3. 3 squared, which is 9, is 1 plus 3 plus 5. 4 squared, which is 16, is 1, 3, 5, and 7. 5 squared, which is 25, is 1, 3, 5, 7, and 9, and so forth. So it looks like the number n squared is the sum of the first n odd numbers. And it can't be a coincidence that these equations hold, so it should be true. And we can actually state that as a theorem. For every n greater than or equal to 1, n squared is the sum. We use sigma notation. 2k minus 1, these are the odd numbers, k going from 1 up to n. So this is a statement that says in mathematical symbols, the nth square is the sum of the first n odd numbers. And the proof uses mathematical induction. What do we get for n equal 1? So the statement, this is my P of n. P of n is the statement that n squared is the sum of the first n odd numbers. For n equal 1, this says that 1 squared, k goes from 1 to 1. 1 squared equals 1. That's true. So assume the statement is true for some number n, some positive integer n. What does that mean? So n squared, therefore, is the sum of the first n odd numbers. Consider the case n plus 1. Well, what is n plus 1 when you square it? When you square n plus 1, you get n squared plus 2n plus 1. N squared is summation, k goes from 1 up to n, 2k minus 1, it's that, plus 2n plus 1. I can write this as summation, k goes from 1 to n, 2k minus 1, and 2n plus 1 is the same as 2 times n plus 1 minus 1. That's exactly what you get if you plug k equal to n plus 1 into this. So this is summation, k goes from 1 up to n plus 1, 2k minus 1. So we proved what is called the induction step. If n squared is summation 2k minus 1, k goes from 1 to n, then n plus 1 squared is the sum, k goes from 1 to n plus 1, 2k minus 1. End of proof. So that is an example of a proof by mathematical induction. Let me give one more example. So what we call a binary sequence is a sequence of zeros and ones. So for example, 0, 1, 1, 0, 0, 0, 1, 0 is a binary sequence. And how many numbers 0 or 1 are there? 1, 2, 3, 4, 5, 6, 7, 8. So we call this a binary sequence of length 8. So we can ask the following question: how many binary sequences of a fixed length n exist? So for example, if n equals 1, there are only 2 binary sequences of length 1, 0 and 1. So 2 sequences of length 1. What about n equal 2? Well, what are the binary sequences of length 2? 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 binary sequences of length 2. What about n equal 3? Let's try and write them all down. 0, 0, 0, 0, 0, 1. 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. No matter how hard you try, you can't find any more. So we have 8 sequences of length 3. And of course, we can notice that 2 is 2 to the first power. 4 is 2 squared, and 8 is 2 cubed. So a nice guess would be there exists 2 to the n binary sequences of length n for every integer n greater than or equal to 1. And that's not just a guess. We can make that a theorem. And we can prove it using mathematical induction. There exist exactly 2 to the n binary sequences of length n. And for the proof, well, first we have to prove it for n equal 1. But for n equal 1, we have 2 sequences of length 1, 0 and 1. So it's true. When n is 1, 2 to the 1 is 1. So let's suppose that the statement is true for some n greater than or equal to 1, must prove the statement when n is equal, for n plus 1. So suppose we have a binary sequence of length n plus 1. We can write it as x1, x2, xn, xn plus 1. And we can divide the sequences into 2 classes, depending on whether this last term, xn plus 1 equals 0, or xn plus 1 equals 1. Those are the only possibilities. So the number of sequences, binary sequences, x1 up to xn, and where the next term is 0, is what? Well, the number of binary sequences of length n is 2 to the n. And this is just a sequence of length 2 to the n with a 0. So there are 2 to the n of them. The other possibility is the last number in the sequence is a 1. And how many binary sequences of length n plus 1 where the last term is a 1 are there? Well, you have 2 to the n choices for this n-term binary sequence, 2 to the n. And whenever you have any binary sequence of length n plus 1, this last digit is a 0 or a 1. Those are the only possibilities. So the total number of binary sequences of length n plus 1 is 2 to the n plus 2 to the n. The sequence is ending in 0 plus the sequence is ending in 1, and 2 to the n plus 2 to the n is 2 to the n plus 1. This completes the proof. So this is a second very pretty example of proving a statement in mathematics and algebra using mathematical induction. This is section 1 of chapter 1 in the notes, and the first part of the homework for Tuesday is some problems on using mathematical induction. So we'll talk about them in the problem sessions tomorrow.